kids went on break, and I went over to Julie's desk and she had a Coca-Cola can. And I took the can, I drank some, thank you. And all the kids are looking like, what's the teacher drinking out of the co-eds? So I had to explain to everyone. She's one of my two beautiful daughters. Well, welcome. I hope you'll enjoy tonight. I've given this lecture in many different venues, from the pulpit, from the lecture, and just from a scientific point of view. Tonight it will be a hybrid of those. I'll bring into it both the religious aspect and the scientific. Religion is very important to me, but what I'll be doing tonight, I think the most important is the scientific, because hopefully what will happen when all is said and done here is that you will have food for thought about either believing or not believing in life after death. And death is something we're all going to face one way or another, and all of us have, I'm sure, because of our ages. Except you, Chrissy, you're so young. And so we either have belief or we don't, or we're struggling with it. But if there is some way in which science can prove or disprove life after death, that would be nice. Especially if you believe in life after death and science proves that it could be so. When all is said and done, I can't prove anything to you. No scientist can. Because every time you answer one question, there are 10 others that pop up. But I'll give you information which to the best of my ability will be all science fact. I won't have any conjecture until right at the end, and I'll let you know when that is, when I start putting together what science says and then what the traditional thoughts of life after death are. But in the beginning, once we start, it'll be all science fact. If you have questions, feel free to ask anytime. Oftentimes, most questions are answered later on in the discussion, so you can ask at the end too. But what I'd like to do is start with a little bit of scripture, but very little. I grew up Roman Catholic, so I didn't know the Bible as well as I might have had I been in another faith. But let me read to you from John, just a very small amount. John, in the beginning was the Word, and the Word was with God, and the Word was God. He was in the beginning with God. All things were made through him. Without him was not anything made that was made. In him was life, and the life was the light of men. The light shines in the darkness, and the darkness has not overcome it. There was a man sent from God whose name was John. He came for the testimony to bear witness to the light, that all might believe through him. He was not the light, but came to bear witness to the light. The true light that enlightens every man was coming into the world. And then from chapter 14 of John, Jesus speaking. Let not your hearts be troubled. Believe in God, believe also in me. In my Father's house are many rooms. If it were not so, would I have told you that I go to prepare a place for you, says Jesus. And when I go and prepare a place for you, I will come again and I will take you to myself, that where I am you may be also. And you know the way where I am going. Thomas said unto him, Lord, we do not know where you are going. How can we know the way? And Jesus said to him, I am the way, the truth, and the life. No one comes to the Father but by me. If you had known me, you would have known my Father also. Henceforth you know him and have seen him. I could pick out many more verses of Scripture, some perhaps which are your favorites. I picked these somewhat randomly. They mention light, and they talk about life after death, that Jesus goes and prepares a place for us. Wouldn't it be nice if that were true? Wouldn't it be nice when our loved ones die, that in fact they don't just pass away to nothing, but they go to some place beautiful, that there is in fact life after this life. You can believe, and the final analysis, it comes down to just having faith. But let's see what science says about the promise of life after death. I'm going to speak to you tonight really about two main things from the science. First will be the work of Albert Einstein. He did many things. His first major accomplishment when he was 26 years old in 1905 was to develop what's known as a special theory of relativity. 10 years later, he developed the general theory of relativity. The special theory, almost everything I say tonight would be based on that, has been accepted for the last 60 years by almost every scientist and every physicist in the world. The general theory, had you asked 35 years ago, some people would say they didn't know. But in the last 35 years, every part of the general theory has now been accepted. It's still theory, and when you say theory, it's just that. But there have been experiments to either prove or disprove the theories, and the experiments which have done has always shown that the theory is true. And again, I'm going to give you all science fact until later on when I say, okay, let's kind of put everything together. The first thing I'd like to do is a common demonstration. We're first going to look at a situation which is common to us and which we would understand, but brings up some relativistic issues. And here's the experiment, hypothetical experiment. This is supposed to be a railroad car, part of a railroad train. And the railroad car, and I'm going to put numbers here just so I can have numbers to talk about. You know, in terms of the calculations, you don't have to do them. I won't lie to you about them as I go. But just to have some numbers to talk about. The train is moving down the track at a speed of 20 miles per hour. And the experiment is going to be this. We're going to take off the side of the train car so you can see it, perhaps a big plate glass window on the side of the train car. And in the train car, we'll put a big long harvest table, which maybe in 3 weeks or so, we can put the turkey on. But a big long harvest table that's supposed to be perfectly flat. I'm trying to hear freehand, it's not flat. And the experiment is going to be for one person to be inside the moving car. I'll take that job for myself. Here I am standing in the moving car. And since the car is moving relative to the earth, I'll be called the moving observer, the MO. And then we'll put someone on the side here, for instance, this young woman, if you would be so kind as to hypothetically stand on the track. She will be the stationary observer. And then we're going to do an experiment. What we're going to do is I'm going to be inside the train, going down the track, and as soon as I line up with the stationary observer, I'm going to take two metal spheres. I'm holding two metal spheres, and I'm going to take the metal spheres, when I come down the track, line up with you, take the metal spheres and push it towards the front and back. You and I are going to observe the motion and calculate the speed of the spheres. Now, the train is going 20 miles per hour, and what I'm going to do is I'm going to push both of these metal spheres with a speed the same as the train, 20 miles per hour in both directions. So we're going to ask me, how fast are these metal spheres going towards the front and back? I'll say 20 miles an hour. Now, in reality, if the sphere was running across the table, it would slow down because of friction. But let's have a perfectly frictionless table, maybe coated with Teflon or ice, so that it doesn't slow down. It just makes the calculations easier. So as soon as I lined up with you, I took the metal spheres, 20 miles per hour towards the front and back. Now we're going to ask you, how fast are the metal spheres traveling? From your vantage point. Well, do you see that to the stationary observer, the sphere which I push towards the back is staying right in front of her because it's moving just opposite the speed of the train. So she says the sphere moving backwards, that I see moving backwards, is moving at 0 miles per hour. But it's staying right in front of her. And the sphere which I said is moving 20 miles per hour in the forward direction, she sees going 40 miles an hour. Because before I pushed it was moving with the train at 20 miles per hour, then I gave it another 20 mile push. So she sees the sphere moving 40 miles per hour. Two observers looking at the same phenomenon. They calculate correctly different speeds. But the speeds are different. So it would say which one is right. Well, I might say the stationary observer is more correct, because she's standing on the stationary Earth. There's more people in the stationary Earth than there is in the train, so maybe she's right. But the answer is we are both right, equally right. Because all motion depends upon the speed of the observer. My reference is to the interior of the car. The stationary observer on the side, her reference is the stationary Earth. Let's take the experiment one step further. Let's calculate how long it will take for the metal spheres to hit the front and the back of the train. Let's say that I'm standing right in the middle of the train, and the train is, just the car, is 40 miles long. That's just this car. Make it difficult to go around corners, I guess, for the engineer up front. But it's 40 mile an hour train car. And I made it 40 miles an hour so the math works out. So, how long does it take for the metal sphere to hit the front and back of the train as far as I'm concerned? I said the metal spheres were moving 20 miles an hour. Well, how long would it take the metal spheres to travel from the center of the train to the front and back? Exactly 1 hour. So I say that the metal spheres hit the front and the back of the train at the same time in exactly 1 hour. But now, you've got different speeds. What does she calculate to be the time it takes for the spheres to hit the front and back of the train? Well, she would perhaps correct my verbiage here and say that actually this sphere here doesn't really hit the back of the train. The back of the train comes up and whacks it, because as far as she's concerned, it's staying still. And how long would it take for the back of the train to go the 20 miles to hit the sphere? 1 hour. And this sphere that she saw going twice my speed, 40 miles an hour, she says it also takes 1 hour to hit the front of the train, because the front of the train has receded down the track 20 miles in the hour, which means it had to go 40 miles, which it does in an hour. So both of us determine that it takes exactly 1 hour for the metal spheres to hit the front and back of the train. But this is what we expected. Actually, this is the first of the two postulates of the special theory, which essentially says everything that you expect to happen with the laws of physics happen with the laws of physics. I can state it more technically if you wish, but that's essentially what it means. But the point to be made here that I'd like to make is that, all motion depends upon your point of view, your frame of reference. Especially, and really only, if there is no acceleration. But have you ever had this experience? You're in your car, you're waiting at a traffic light, and there's a lane of traffic to the left, a lane of traffic to the right, and you're waiting for the light to turn green, and all of a sudden you feel yourself going back, and you put your foot in the brake. You've got your foot in the brake. Hey, you're not moving backwards, the guys beside you are edging up. And you swear you were moving backwards. Because if there's no acceleration or deceleration, speeding up or slowing down, you can't tell motion. Motion depends only upon your frame of reference. So here, even though the two observers got different speeds, we had a different frame of reference. Because the motion of any object depends upon your point of reference. For instance, you're on Route 495, going 65 miles an hour, and someone passes you going 75 miles an hour. To you, it looks like they're going by you with the difference between your speeds, 10 miles an hour. But have you ever had a flat tire on the side of a road like that? I hope you haven't. I hope you never have to. But have you ever been stationary on a road where people are going fast? Those are the guys going 55. They're going by you real fast because they are going 55 because you're standing still. But when you're going 65 and someone passes you going 75, it kind of just looks like they're lazily going along. Because the speed of any object depends upon your speed as the observer. Except the speed of light. And that is the second of the two postulates of the special theory. The speed of light does not depend upon the speed of the observer. Light goes by you as fast as it goes by anyone else, no matter what their speed is. Now, Einstein said that. He proved it with the mass equivalence statements that he made. But right now, I'll just take it that I'm telling the truth from Albert Einstein, that the speed of light does not depend upon the speed of the observer. That's the only thing for which that happens. Well, while I was waiting, I took all my art skills and did another picture. You can see all the art skills that Allison and Juliet didn't come from my side. I did this really nice, though, isn't it?
Very good.
Again, a train car moving down the track at 20 miles an hour. And we're going to do a similar experiment, miles per hour, except this time, instead of rolling metal spheres across a flat table, I'm going to stand in the middle as a stationary observer. Here I am. And I'm going to take a light. Here I am holding a lantern. And instead of rolling metal spheres across the table, I'm just going to stand in the middle of the train and turn the light on. And you're going to be standing on the side, the stationary observer. I'm the moving observer. And we're going to do a similar thing. Now, in order to do this, we couldn't do it with our naked eye because it would all happen so quickly. But if we had instrumentation that would be in a simple physics lab, like in a high school or a junior college or college, we could make these determinations very easily. Here we go. I'm in the car. Black's in the side of the car. The inside of the car is all dark. I got all the lights out. I move down the track, and when I line up with you, I turn the light on. Okay, the light comes out of the light source, and as before, we calculate the speed of light. Well, if we're in a vacuum, it would be 186,000 miles a second. And I would say that's the speed of light going towards the back of the train and going towards the front of the train. Let me write it a little bigger. 186,000 miles per second. Now, that's not miles per hour, that's miles per second. We, as humans, have never got any person to go that speed. The only thing we've got close to going that speed are subatomic particles, electrons, and so forth. So, I'm in the car's dark, I line up with my friend, I turn the light on, the light goes towards the front and the back, and I calculate the speed of light. That's, according to me, inside the train. Now we're going to ask you, as a stationary observer, to calculate the speed of light. Before, the speed of the metal spheres was a function of the speed of the train. Here, though, the speed of light is not. The stationary observer would say that the light is traveling exactly the same speed towards the front of the train as I see it, and towards the back of the train as I have calculated it. Now, you would expect her to say the light going towards the front is 186,000 miles per second plus the speed of the train, plus 20 miles an hour, because that's what happened with the metal spheres. And the light going towards the back of the train would be 186,000 miles per second minus 20 miles an hour. But she doesn't. She says exactly the same speed I say. Because the speed of light doesn't depend upon the speed of the observer. Now, footnote. You might be saying to yourself, come on, Ron, 186,000 miles per second compared to a train going 20 miles an hour, you wouldn't be able to tell the difference. Yes, you would. Next time a policeman stops you with a radar gun going 45 in a 30 mile an hour zone, and you have to pay the ticket, guess what he used or she used to determine your speed? Radar. And radar is electromagnetic energy, it's light energy. And so the next time you get, and I hope you never don't get one because you don't go at speeds higher than postal, if you ever got one or will get one, think about it. They just were able to tell if you were going 15 miles an hour over the speed limit using light. So, Einstein said this would happen though, because the speed of light does not depend upon the speed of the observer. There is nothing else but light for which this happens. Metal spheres rolling across tables or anything else, only light. But now let's take this experiment one step further, because now we're going to get something interesting, because now we're going to determine how long it takes for the light to hit the front and the back of the car. Or rather, because that time is so small, we'll go through the sequence of events that would occur in this hypothetical experiment, where we do the experiment and both the observers, me in the train and the stationary observer, are going to say when the light hits the front and back of the train. So let's start the experiment again. Everything's in darkness. I get in front of you and I turn the light on. Here's what would happen. This would happen in the twinkling of an eye. We could tell using instruments from the lab that this is what happens. So I turn the light on, and here's now what happens. The light goes out. I say, the back of the train's lit up. I see it light up before she did. Why do I see the back of the train light up before she did? Because to me, the back of the train is coming towards the light source and has to go a shorter distance. So I see the back of the train light up before she did. What this means is that really, in terms of layman's parlance, everyday talking, what that means is she's looked into my future. Because she sees the back of the train light up before I see it light up. She's looked into my future. If there was a big sign there, Ronald Coelho is a fink, and she saw it right it, she might start laughing. I don't know what she's laughing about. She sees the back of the train lit. She is now looking into my future. Carry the experiment a little farther. The train goes a little farther down the track. Now I would say, front and the back train light up simultaneously. At that point, I'm seeing the back of the train light up. She's already seen that, so I am looking into her past. I am also looking in her future because I see the front of the train light up before she sees it light up. Why is that? Because the front of the train is going away from the light source. Then finally, when the experiment, the front of the train lights up, and she says it. At that point, she's looking into my past. Would this happen? Yes. Has it been proved? Yes. As a matter of fact, it's a very important statement in the special theory, that the simultaneous occurrence of events, simultaneity, which is not often noun, meaning the simultaneous occurrence of events. The events I spoke of here is the light hitting the front and back of the train. Simultaneity is relative. It depends upon your speed through space. Because our speeds were different, we would have, at least hypothetically, seen difference in when the lights hit the front and back of the train. Now this sounds like science fiction. But if something occurs for you and I right now, because we're all moving at the same speed through space, to other observers who are moving faster, it may occur at a different time. Or to others who are moving slower, it would occur at even a third different time. Second different time, third time. And that doesn't seem right, because either something happens or it doesn't happen. But when we observe it, it depends upon our speed through space. Has this been proven to be true by experiment? The simultaneity, the simultaneous occurrence of events is relative? Yeah. Now, what can you use this for? Well, I don't know. First of all, the theory tells us some things that cannot happen. First of all, the theory says, at least does not indicate that you can go backwards in time. Once you've gone through time, that's it. The theory also says that in order for anyone to see something, it must have happened. You may not see it till later, but it must have happened. But other than that, the theory is wide open. Does this explain déjà vu to us? Do we, in fact, when some people have experience with déjà vu, are they, in fact, experiencing something that someone else, themselves, for instance, will see at a later time? No one knows. But the whole idea that when something happens, everyone has to see it at the same time, it's not true. We know it's not. Okay. Well, the simultaneity being relative, that sounds kind of science fiction. So let's go on. Because the idea of simultaneity being relative and the idea that you were looking into my past and future and so forth depended upon the speed of light not being invariant upon the speed of the observer. Remember, speed of light doesn't depend on how fast we're going, unlike any other object. How can that be so? Well, let's do a little experiment here, hypothetical experiment. The town doesn't mind if we set up a rocket base up the top of the hill, does it? Or the hill spaceport. And so, here we are, on top of the hill, and we've got a rocket ship. And we're going to put, we'll put Julie in here. Julie, sorry you're in there, right?
It's okay, yeah.
Okay. Because I'm going to make fun of you, that's why I didn't pick anyone in here. So what's new, right?
Right.
And here we are, standing beside the spaceship. And at 8 o'clock tomorrow morning, this spaceship's going to take off and go through space. And it's going to travel in this direction, so here it is up here in space. Hi, Julie. And it's traveling in that direction. And the speed that it's traveling is almost the speed of light. The speed of light is 186,000 miles per second. And that's miles per second. The rocket ship is going to go almost that speed. The speed of the rocket ship is equal to 184,000 miles per second. You see how the rocket ship's almost going the speed of light? Just 2,000 miles per second less. Now, in order to get an object like a rocket ship going this fast, it would take a long time, at least with our present technologies. And we don't have a way of getting a big sized craft like this going this fast. The only thing we can get going this fast are subatomic particles. And that's where all the work's been done, because they're real small, and with accelerators they can get them to go fast. But someday we'll be able perhaps to get a rocket ship to go this fast. And I'd also like you to give me a little more leeway in this hypothetical experiment, because you've seen rocket ships take off. They roar and give off all kinds of energy and then slowly lift off the pad, and hopefully everything goes well, and they go faster and 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 faster, and then get to a speed where they can escape, if they're going to escape the Earth, escape the gravity of the Earth and go off on their way. So it takes time. But for our discussion here, to make this simple, I'm going to say that the rocket ship Julie's in is a magic rocket ship, in that the instant it takes off, it's going its maximum speed. Actually, this would take years to do it, if we could do it. But let's say the second after it takes off, 8 minutes, 1 second, she's going her maximum speed, which is this. There's her speed. See, 2,000 miles per second less than the speed of light. Here's the experiment. Back on Earth, so she's not, the rocket ship's not on Earth anymore. Back on Earth, we're going to take a laser beam. I'll make it look like a flashlight almost. You're somewhat familiar with lasers. They are sources of light in which all of the beams travel perfectly parallel, so they never spread out. So there is a laser beam, and I'm going to shine the laser beam right beside her rocket ship. And the experiment's going to be this. We're going to calculate how fast the light from the laser beam is coming out of the stationary laser emitter. And then Julie up here, the rocket ship, is going to determine for us how fast the light is going by her rocket ship. So, back on Earth, how fast is the light coming out of the laser mechanism? The speed of light, 186,000 miles per second. Now we're shooting the light right in the same direction as Julie's rocket ship. And we say to Julie, okay, calculate the speed of the light going by your rocket ship. Can you see that we would expect her to say the difference between the two speeds? We'd expect her to say the light's going by the rocket ship 2,000 miles per second. That's what she says. She says, okay, I'm ready to give you the speed. Okay, what's the speed of light? I'm very small, I apologize. What's the speed of light going by your rocket ship, Julie? Got it? Yep. Okay, what is it? It's going by my rocket ship, she says, at 186,000 miles per second. Damn it. That's not what we expected. Julie, so I know she didn't make a mistake, so I said, Julie, check your calculations, come on. Because we all see what's wrong. See, the light's going by her rocket ship at 186 meters per second. That's what she says the speed is going by her rocket ship, but her rocket ship's almost going the speed of light. How can it be going by her at the same speed it's going by us if she's almost going the same speed as light? So we've asked her to check her work, and she says, I still get 184,000 miles per second. Now, what's going on here? Well, let's go back to the drawing board, so as to speak, and talk briefly what speed is. Speed is the distance that something travels, in this case the light, divided by the time it takes to travel that distance. Like it's 30 miles from here in Boston, it takes an hour, and then you've gone 30 miles per hour on average. You take distance divided by time. What would we have given Julie to measure speed? Well, probably some kind of sophisticated apparatus that would have cost a lot of money. But no matter how sophisticated the apparatus was, essentially what would give her is a thing to measure distance, like a meter stick or a yardstick, and a stopwatch to measure time, because that's what she has to measure. And so the way she would do it, she'd say, okay, this is Julie. I'm going to calculate the speed. She measures the distance that light travels, say from here to here. She measures that distance with a meter stick. To her it measures 2 meters. And she measures the time it takes to move. So start the stopwatch, stop the stopwatch. And she measures the time, and she put that into the equation and got this much bigger answer than we expected. We only expected her to say 2,000 miles per second. She says 186,000 miles per second. And she's right. She hasn't made an error. Well, what the heck could be going on here? Well, what's going on here, and it's one of the things which is, again, going to sound like science fiction. This is going to sound like crazy, but it's not. It's part of Einstein's theory. It's perfectly well accepted. Let's see if there's something happened to her measuring instruments. Because you see, myself, and probably you, think that some things in the universe are rock solid, that they can't change, that they're gospel. And yet, let's look what happens here. Because she is going close to the speed of light, actually this is approximately 99% the speed of light, there have been changes in her environment and in her length measurement and time measurement. So we'd say to Julie, Julie, you know that meter stick's a little bit bigger than the yardstick. So if you know what the yardstick is. Julie, take that meter stick and put it out the window. It's like this, when it left, you know? She sticks it out the window and it's 1/7. It's like this big. I'd say, come on, Julie, the meter stick. She'd say, that is the meter stick. It's shrunk. Well, if her meter stick is shrunk, then when she used her smaller meter stick to measure this distance, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, can you see she'd get a bigger distance? And if she gets a bigger distance, that would explain the speed that we're looking for. Because she says it's 186, we only expect 2,000. So her measuring instrument has changed. Looking at how the meter stick has shrunk relative to us, as we see her meter stick, that accounts for about half it. We'd say, Julie, take that stopwatch out we gave you, will you? And give us 2 seconds. She'd say, okay, ready, your mind, get set. Julie, 2 seconds. I know, hold your horses. Don't talk your father like that. 28 seconds later, she says, time's up. I'd say, what do you mean time's up? It was only supposed to be 2 seconds. She says it was 2 seconds. Her watch said 2 seconds. Our watch said 28 seconds. Why? Because she was going close to the speed of light. And for anything that goes close to the speed of light, time slows down. It actually slows down. Can we prove that? Yeah. Have we proved it? Yeah. Is it known theoretically? Yes. And practically. So time has slowed down for her. And we'd say, Julie, don't you notice that everything's going slow? She'd say, no, because she wouldn't notice. Because everything is in concert with one another. She'd say, as a matter of fact, you guys are running around like chickens with your head cut off going 14 times faster than you should be. So, all right. So there's been a contraction in length and there's been an expansion, a dilation of time. Well, it's now 12 o'clock and I don't know about you, but I'm hungry. It's lunchtime. So we say to Julie, Julie, 4 hours gone by, let's break for lunch. She'd say, what do you mean break for lunch? She'd say, oh, it's 4 hours since you took off. She'd say, no, it isn't. To her, it's like 28 minutes past 8. And so all the food that she ate earlier is still in her stomach. It hasn't digested. Because you see, everything slows down, not just your watch, but all the biological functions. We're almost near the end of the theory of relativity.
Dad,
Yes.
is she still going 184,000 miles per second?
Yes.
Or is she at, okay, so she's very close to the speed of light, not the
Yes.
speed of light.
Yeah, not. And you'll see why I say not. But yes, she was going 99% speed of light. Einstein developed equations to tell us this. I'll just show you a couple. For instance, the time equation, T equals T naught over the square root of 1 minus B squared over C squared. Pretty technical if you first look at it the first time. But T naught is the time interval that Julie experiences. T is the interval that we experience, the longer interval. But what would happen, and I'll give you the equation for length. Length equals L naught times the square root of 1 minus B squared over C squared. By the way, V is the speed, I just try to erase the whiteboard. V squared is the speed of the rocket ship, and C is the speed of light, and they're squared. So it's the speed of the moving object divided by the speed of light squared. These equations show us that there is a decreasing length between 2 points the faster you go. Length contracts in the direction of travel, and time expands. And if later on, if you want me to substitute and show you these equations more clearly, I will. But what would happen? What would happen if Julie went the speed of light? What would happen to time for her, and what would happen to length for her? Well, in this equation, say 1 second the time that she would see would be equal to, say, 1 second of time divided by the square root of 1 minus her speed squared over the speed of light. If Julie went the speed of light, if her rocket ship could obtain the speed of light, then this factor here would be 1 minus C squared over C squared. C squared over C squared is 1, so that what's under the square root sign would be 1 minus 1. 1 minus 1 is 0. And what's anything divided by 0?
0.
Anything divided by 0 is infinity. Because when you keep dividing something by a smaller amount, the quotient, the answer keeps getting bigger. When you divide something by 0, it becomes, well, sometimes we say undefined or infinity. It's infinitely big. So if Julie and her rocket ship, or you, or any of you, or any of us, were ever to go the speed of light, any interval of time, 1 second, 1 year, 1 eon, would last forever. Because time would stop. If you go the speed of light, time stops. Also, if you go the speed of light, length contracts to 0. So if you were to ever go the speed of light by standing at one point in the universe, you would be at all points, because length would contract to 0. And this third part I didn't tell Julie before I asked her to go on the rocket ship. Length contracts as you go faster and faster. When you go the speed of light, it contracts to 0. Time slows down as you get close to the speed of light. When you go the speed of light, it becomes infinitely long. This is the part I didn't tell you. The third change is a mass change. Mass is a measure of the stuff in your body. We measure mass by our weight here in the gravitational field of the Earth. But as you go faster and faster and faster, the mass of your body increases. So as you went faster, you'd weigh more and more and more. I'm actually doing an experiment with that. But so if Julie went the speed of light, or any of us went the speed of light, we would become as massive as the universe. We would become the universe. These are the statements of Einstein's special theory of relativity. Almost done with theory, and we'll take a quick break. This was all special theory. The general theory in 1915 deals with systems that are accelerating relative to one another, going faster or slower. And the general theory explains gravity being a curvature of space, and so forth. But what also comes out of the general theory is what's known as the twin paradox. Susan and Sally Peller paradox. My first wife was a twin, right, Susan? The twin paradox. Now, often when the twin paradox is written about, they don't even tell you about the paradox. They tell you about what leads up to it, but they never get to the paradox. We've done this twice in Time magazine, once years ago and once a couple years ago, about 10 years ago, about 30 years ago. Here's the paradox. Here's Earth, and I'm going to take two astronaut sisters, twin sister A and twin sister B, and they will be 30 years old. And twin sister B is going to get into the astronaut field, and she's going to be chosen for the first flight to leave the Earth and go to the star that's closest to the sun. Our sun is a star, but the star closest to the sun is Proxima Centauri, Alpha Centauri. So the twin B, I guess for Bucher, the twin B is going to get in the rocket ship. She's going to accelerate the rocket ship so she's close to the speed of light, say 0.999 the speed of light. And she's going to go to a star called Proxima Centauri, and then she's going to go around that star and come back home. Now, if she went the speed of light, it would take 4 years to make the trip to the star and 4 years to get back. So a little over 8 years. So, the experiment's complete. The sister, the twin sister who stayed on the Earth, has aged 8 years, because that's how long it took for the total flight. So she's now a woman 38 years old. The twin that was in the rocket ship, she comes back, and she's still a 30-year-old woman. She's probably 30 years and 2 months old. She's still young. How can she still be young? Because time slowed down for her. Because she was going close to the speed of light. Time slowed down relative to the one who didn't go close to the speed of light. So this woman comes back, she's a 30-year-old woman. Her twin sister's a 38-year-old woman. But that's not the paradox, and that's usually where people stop. But that's not really the paradox that Einstein talked about. The paradox is this. See the woman who was in the rocket ship? She had to get close to the speed of light, accelerate away from Earth, then decelerate, slow down, then go around Proxima Centauri, then speed up again, and then decelerate. Have you ever seen pictures, although I haven't seen them for a while, of rocket ships taking off from the Earth, from the back of the rocket ship? They have a movie camera going, video camera, and there's a big flash of light, but then, after the big flash of light, and the rocket ship is moving away from the Earth, like for the lunar landings, it looks like the Earth is moving away from the rocket ship, because you don't see any fire or anything. And if the lunar craft, in this case, this rocket ship, accelerated and then went a constant speed, the woman in the rocket ship would say, hey, wait a minute, you know what they're doing? All these guys, these NASA guys, they're fooling me. What they're doing is they're moving the Earth away from me and bringing Proxima Centauri close, and then moving Proxima Centauri around me, and then bringing the Earth back to where I was. Because you remember that all motion depends upon your frame of reference? And who can tell who moved here? If in fact, it depends upon the frame of reference. And who can tell who aged? And why did one age and not the other? If you can't tell who was moving. The answer to it from the general theory is just who accelerated or decelerated. Who changed their speed? Because it's during the acceleration-deceleration process that these changes occur, that these aging processes occur. And so it's hard to tell who moved, viewed from the two laboratories, viewed from the two positions. But in order to tell which one aged, just say which one went through acceleration. The one that went through acceleration did not age as much as the one that did not go through acceleration. So the paradox here is they both should be the same age, but only one accelerated, therefore only one had time going slower. So, to recap, theory of relativity, general and special. When an object goes faster and faster, changes occur in it. Changes occur in time, length, and mass. And if an object goes the speed of light, any object, you or a subatomic particle, or your mother, or your father, if they go the speed of light, then three things are going to happen to them. A, time stops for them. B, length contracts to zero for them, being at one point they're at all points. And C, they become as massive as the universe. Those are the three statements from Albert Einstein. And we'll see how those apply to an explanation of what happens when you and I pass from this life. Let's take a quick break in case anyone needs to get up and walk around, just a 5-minute break.
Good question.
Yeah, well, okay, question.
Twin B,
Yeah.
she might be years younger, but is she big fatty now? She's come back?
I hope so. Actually, one thing I didn't mention, you might say, well, the twin that went, 8 extra years of life approximately, but she actually didn't. If you ask the one who was in the rocket ship, hey, great, you're only 30 years old and you were gone 8 years, she'd say, no, I wasn't gone 8 years. I was only gone 2 months. Because to her, everything slowed down. So she only had, 2 months of dinners and breakfast. Notice what I'm so to her, it was regular time. But let's hope she did get fat. So her massive, she became as massive as the universe.
She's almost as big as the universe.
So about 5 minutes, we'll come back.
Okay.
You all right?
Are you comfortable?
We've talked about theory of relativity, and to the best of my ability, all that was what Einstein said. It's all been proven. But now I'd still like to talk about science fact until I get to the end, near the end. But I'd like to now talk about the physiology of the human brain. Before I talk about the human brain, which is the organ, we think the brain is the place in the body, as you know, where our mind is situated. And when we talk about our mind, that's a little bit of more of a nebulous thing than talking about the brain, because your mind is a very complicated thing. And another word for your mind would be your soul or your personality. But everyone has a unique mind. And what we love in people whom we love is their mind. Bodies attract us one way or another. But what we really love and cherish in someone we love is their mind. Your mind is mostly held in the brain, maybe a little bit in the cortex, the brain stem, but mostly in the brain. And the brain is an organ like the liver and the heart and so forth. The brain is protein and mostly fatty tissue. Someone called you a fathead, they might have known the physiology of the human brain. But in your brain, as far as we know, the brain works pretty much like a binary computer. There are on-off switches, and those on-off switches go on and off, and they record memory, very similar to what happens in a digital experience in electronics. And so what your brain is really a series of switches. These switches are all organic. They are nerves and nerve impulses. But right now, as you're listening to me and trying to understand what I say and relating it to life's experiences, if we could look inside your brain, there would be literally billions and billions of flashes of light going off. And what these flashes of light, we think, are the way in which nerves move from one neuron to another. That's the way in which our body takes the information, processes it, and stores it, and then sometimes gives it back out. So if we could look into your brain or mind, we would see it as really a beautiful matrix, a beautiful arrangement of little flashes of light. These flashes of light are technically called photons. Photons are the little bundles of energy which light energy travels in, whether it's visible light or infrared heat energy or X-rays or ultraviolet light or radar or whatever. And so right now, in your brain, you have all these photons of light flashing. When a photon flashes, it actually moves what's known as an orbital to one side or another. That allows electrical impulse to go through, and then that electrical impulse makes eventually a current, like it does in a video camera or on a computer, and that's what's up here. And as time goes on, we store this information. Sometimes we lose it, but we store the information. So your mind, your personality, your soul is really in your brain. How do we express what's in our mind, what's in our soul to someone else? Well, while we're living, the only way we can express to others what we feel, what we think, is through the bodily senses. Seeing, touching, feeling, tasting, smelling. Now, you know, my wife and I, we can use all of those. Right now, all I can do is let you hear me, let you see me gesture, and that's it. But the only way I have to get my mind to you or you to me is through the bodily senses. And as long as I'm living and you're living, in a sense, we are prisoners of our body. Because if the only way I can tell you what I'm thinking or what I feel is through the bodily senses, then unless I'm able to use the words to express what I feel, or touch you in the shoulder just the right way, or look at you in the eye and give a smile or something, if I can't go through those human gestures well, then I can't tell you what I'm experiencing. And so, I'm sure you've been in situations before where you said, geez, I wish I had said that, and I wish I had given him a hug, and you didn't. You wanted to. You wanted to tell someone what you thought. But you and I are living beings. We're human beings, and we can only give the information through our bodily senses. Now, these bodily senses, hearing, smelling, tasting, feeling, I missed a couple. They are quantized. That is to say, they only work in certain energies, in certain areas. For instance, light energy. Radio waves are light energy. Microwaves are light energy. Heat waves are light energy. X-rays, ultraviolet rays. They're all light energy. The only part that you and I have been given by God ways to see is a very small part of the overall light spectrum, as it's called visible light. We can see colors from red through orange, yellow, green, blue, indigo, and violet. After violet, we can't sense it. It's called ultraviolet. Below red, it's infrared, we can't sense it. So in terms of seeing, we can only see a very small range of what we know is out there. In terms of hearing, when we were young, before we started listening to rock music, or before the grandkids came, we probably could hear 20 to 20,000 cycles per second. Probably not so now. We're getting old, we listen to loud music, and we have hearing aids that don't work. I don't know where we wear them. But you see, there are sounds in this room right now that you and I can't hear. The dogs can hear them. I used to take one of my dogs, what was that first dog? Schultz. Used to take Schultz into the new school that was built, and he'd only did it a couple times because he'd want to make it his territory, if you know what I mean. So just a couple times, but he'd go in, and I remember he'd look up at the ceiling as though he was hearing some sound. I didn't know what it was until the air conditioner started breaking, and then I could hear it. But he was hearing sounds that no one else could hear, and that's why, you know, ultrasonic whistles for dogs. There are a lot of things in this room right now that we can't see, hear, touch, taste, smell, or feel. There are people singing and dancing in this room right now. I didn't have that much wine out there, so I'm not drunk. There are people singing and dancing in the room. And you say, how? I'll say, well, let me get a TV. I can't see it with my eyes, neither can you. But let me get a TV, not a cable setup, just an antenna that just picks up what's in the air. And all those signals are here, but you and I can't see them. There are sounds we can't hear. There are smells we can't smell. When you touch someone too lightly, you get no feeling. If you touch them too hard, it hurts and all the impulse places are gone. So all of our bodily senses are only from the bottom threshold to the top threshold. Below and above those, no sense. And that's too bad, because there's a lot more out there that we can't see, feel, touch, smell, taste, and so forth, than we can. We're very limited in what we're able to discern. Now, just because we can't see, feel, touch, taste, or smell something, just because we can't see it or feel it, taste it, does that mean it's not here? Well, it could be that it's not here, but probably, since we know there are more things in this room right now than you and I are experiencing, the best guess is that if you can't, sense something, all we can say is, I can't sense it. Not that it's not there. It's just that you cannot sense it. Now, our brain is a series of millions and trillions, and literally trillions and trillions of little snatches of light, little photons. Usually, by the way, in the ultraviolet and infrared region. When you and I are living, what keeps all those photons in our brain? Because they're there, unless we lose all our knowledge. Some of you have taken biochemistry before, maybe you talk about ATP and ADP and all that stuff, and talk about how it works biochemically. But the bottom line is, if you ask, I can't think of the person, a neurologist, you ask your neurologist, what holds all those photons in the human mind when we're living? Because I asked two of them at parties, kind of similar to this, and I try not to go up to someone that, especially if I don't know them, and start talking shop. We don't do that. We're here to have fun. But a couple of times I did that with people who I knew. One was a neurologist and one was a surgeon for nerves. And I kind of bullied both of them, and I, kept asking. I said, the brain is a matrix of photons. Yeah, they'd say, yeah. And, they're nice to me. But I kept bullying them. And one of them actually got mad when I said, what holds the photons in? Because there's nothing to hold the photons in. There's no insulation wrapped over us. There's nothing there except some skull bone and some hair. That's it. And these don't insulate for the photons that are in our brain. So I asked, what keeps them there? And finally one guy had enough of me, and he said, don't you understand it's a blanking miracle? I said, that's exactly what I wanted you to say. Like the miracle of life. Yes, it's miracle life, damn it. I said, come on, let me buy you a scotch. Because it was an open bar. So, and the other fella said the same thing. They don't know. They don't know what keeps us alive. I mean, the biochemistry tells about all kinds of energy transfers and so forth. But what keeps all the radiation there, all these little photons of light, no one knows. They have to finally say, until they know more, it's a miracle of life. And you and I right now, since we're living, we're experiencing the miracle of life. Gracious be. All of what I've said is science fact. I haven't prevaricated and haven't lied in any way. But now what I'd like to do is take the science fact and put it with some statements, some conjecture about how these things that we've talked about can explain life after death. So from here on, it's conjecture. What happens when someone dies? All of us probably have had someone die whom we love, whom we knew. And when someone dies, it's terrible. Because if you can see them in the casket, that's not really the person you knew. They're cold. You can't talk to them. You can't whisper in their ear. You can't even touch them. They're cold. You can't use any of your bodily senses. And so when someone dies, you can't communicate with them. And if you can't communicate with something, you might say there's nothing there. Like trying to communicate with a stone. You can't communicate with it. It's cold. It doesn't respond. And so when someone dies, the easy thing to say is that it's all over, it's gone. The person whom I loved and cherished, they died. They're not here anymore. I enjoyed them when they're here. Death is death. And some people take that to be the situation. But if I ask them, why do you say that upon death there is nothing? They're probably going to say, because I can't communicate with a person anymore. You mean you can't speak with them? No. You can't smell them anymore? No. They can't talk to you? No. That's why they don't believe there's anything there. But boy, I'll tell you, if someone gives me that to be the reason why they think of the finality of death, I want to say, boy, I'd like to bet against you. Because for a betting person, that's a very poor excuse. Because as I've alluded to, and if we took some chemistry and physics courses, you'd know more of this, that there are many more things around us than those that we can sense. And just because I cannot communicate with a person who has died, all that means is I can't communicate. It doesn't mean they're not there. It's just they're no longer in a place where I can communicate. So if you base the finality of death solely on the fact that the one whom you loved and knew is not, you can't communicate with them, you can say that, but that's logically not a good statement. So, what happens when we die? Well, what if there still was something? What if something persisted after we die? After the heart stopped beating? Well, we know that the brain waves are going to decrease. You can see them with a graph. You can see the brain getting cold as well as the rest of the body. This thing that held your mind is going to start decaying, dust to dust. So when you die, the brain's not you anymore, it's not your loved one anymore. What could it be? Well, what if upon death, and this is a big what if, but what if upon death, the photons, which are your brain right now, which are your mind, your soul, your personality, what if upon death, all those photons stayed together and didn't dissipate and cool off and go to nothing? What if all those photons stayed together? Well, some of the physicists would say, how can they stay together? Physically impossible. You'd need a miracle. Like the miracle of life? You and I are experiencing the miracle of life. Can we not perhaps begin to accept that there is a miracle of death? That when we die, these photons of light, which are you and I right now, do in fact persist and stay together and leave our body. Our body's been a prisoner to our mind because we can only express what the body senses. If they stay together and leave our body, if they leave our body and leave the matrix of the brain, then they start to go the speed of light. So if when you die, the photons of light leave the matrix of the brain and then would start moving the speed of light, if they move the speed of light, look at the three things that would happen to it according to Albert Einstein for anything that goes the speed of light, and see how these correspond to the classical views of what's supposed to happen in the next life, what's supposed to happen in heaven. If your mind or the mind of your loved one who's passed before you, if those photons stayed together and would go the speed of light, which they would, three things happen. First, time stops. That's a promise in almost every promise to heaven, that time is no longer variable. Can you imagine time stopping? Now some people say, I mean, terribly, I mean, I have to be with these people forever. No. Pick the best people you love in the world and think of being with them forever. Now, how much is time a problem for you and I? It is. Because if I spend time with Allison, I take it away from Julie. If I spend time with Julie, I take it away from my son. And when my mother was here, if I spent a lot of time with my mother, I couldn't spend it with my mother-in-law. You and I right now have always got a problem. Everyone I know has a problem with time. Christmas is on the way. Come Christmas morning, I'm always melancholy. Because I know the kids are going to come over, the grandkids are going to be a great day. But maybe he's crying because he knows that around 9 o'clock everyone's going to go home. And I may never see them again. so I'm melancholy. And I say, don't be melancholy. Come on, have fun. And I try to have fun. But I know time is fleeting. And I spend a lot of my time worrying about time. I'd love to just sit down with my friend and sit there and have a nice wine and not worry about, gee, I'm neglecting my wife or something. Or spend time with my wife and say, geez, I'm neglecting my kids. Imagine a place called heaven where time is no longer a variable, where you can spend as much time with a friend as you want and not take away from another. The beauty of heaven, a promise. Second promise in heaven, pretty much universally for every religion, and I'm not a theologian, but I've studied, the Christian and the Jewish and the Mid-Eastern religions and the Far Eastern religions, most of them, not all of them. But almost all of them have the same final statements to heaven. First was time stops. Second is, in heaven you want for nothing. That's a promise. Well, how much less could you want for nothing? But as Einstein said, if your mind went the speed of light, length contracts to zero. If length contracts to zero, when you die, your mind would be in a place where by being at one point, you're at all points. So, I want to go to Hawaii this afternoon, I'm there. I want to go back to be with my mother in West Bridgewater, I'm there. I want to go with my grandson in Grafton, I'm there. I want to go with my daughter in Lakeville, I'm there. I'm at every place. I want for nothing. Imagine being at every place at once. There's nothing else to want. And the third promise of heaven, this is the one I have the most trouble with. But the third promise of heaven is that in heaven you see the Creator, and you become the Creator's universe. Well, I thought long and hard about that, and the only way I can reconcile that promise is the statement from Einstein that says, if you go the speed of light, you become as massive as the universe. Maybe when we die, although we keep our individuality, we become God's universe. And how much more brothers and sisters can you and I be of one another, except to someday find out we are, in fact, all together in this. We're all His universe, God's universe. Those three statements are almost every statement of the promise of life after death. I find it interesting that Albert Einstein, who professed to be an agnostic, someone who didn't believe in a God, didn't believe in what God did. When you read his works, though, that's not really true. That's what other people wrote about him. But a man who, said he didn't believe much in life after death, and yet perhaps gives us the blueprint for explaining to us what it's going to be like and how it can be. There are so many things we as scientists, I'm a chemist, but there are so many things that we as scientists don't know. And what we know is we know very little. And the only thing I can do is to say I trust. I trust what was written in John, that there is a place for us, and someone has gone to prepare that place. Yeah, it's only something written in a book. But Albert Einstein, in the modern day view of the physiology of the human brain, says, yeah, it can work. Here's how it works. Is it true? Obviously, I think I know it's true. And when I pass away, I hope that I won't be scared. And I hope I'll have a big smile on my face. Because I hope to see all the people who have gone before me and really see that heaven. I won't have to buy watch batteries anymore because time stands still. There are all kinds of things we can talk about. I'll open up for questions. I don't know if you have any, but I'll be glad to discuss them. And actually, we can discuss them over wine. So we can break out.
Thank you.
Thank you. Hope
Thank
you
you.
enjoy.
Thank you. Well done. Thank you very much.
You believe. Nice group. I assume the Tar and Feathers is out here.
Come join us. That's a beautiful
I want to take out a whole meeting.